Hello everyone, our project is to implement a smart parking system using wireless sensor network. In this screencast, we aim to explain you briefly about our project, why we chose the decisions which we had to choose, and their implications. With the rapid increase in the population nowadays, the number of cars have increased tremendously. This has led to heavy traffic congestion as well as difficulties in identifying parking spaces. The only solution to this problem is designing an intelligent parking system. How can such a system be realized? Installing video cameras is one of the traditional approaches, but these traditional approaches are too costly or inefficient or way too expensive, and these are also not so user-friendly. With the advent of wireless sensor networks, the above-mentioned problems can be mitigated. The advantage of using wireless sensor networks over traditional methods is that they bring in flexibility, scalability, and hassle-free maintenance to the network. They can also be made user-friendly by connecting to smartphones as well as mobile applications. They are also cost-effective and easy to maintain. We have considered the following application scenario: an indoor parking lot which has multiple parking slots wherein each slot has a wireless sensor node, which is denoted by the black dot. This node, hereby referred to as a leaf node, consists of a magnetic sensor which detects the presence of a car due to the change in the magnetic field. While designing the network architecture, we have considered two possible scenarios. The first one where each node sends its data to the base station directly. The main advantage of this approach is that it is simple to implement, but the serious drawback it has is that it consumes a lot of energy to transmit since the distances between the nodes and the base stations are quite high. In the second scenario, each node forwards its data to its neighboring nodes, which in turn forward it to their neighboring nodes, and the process is repeated till the data finally reaches the base station. The disadvantage of this approach is that when network is large, it is quite complicated to implement and often the data might be lost. To mitigate the disadvantages in the above two processes, we consider a hybrid approach which is implemented as follows. Each parking lot has a sensor node which has a magnetic sensor. This detects the entry or exit of a vehicle based on the change in the magnetic field. This node is called as leaf node. These leaf nodes are deployed in large numbers and are usually energy constrained. Several of these leaf nodes are grouped together to form a cluster which is often called a head node. The leaf nodes forward their data to the head nodes, thus forming a single hop network. Many such head nodes forward their data to the base station through multi-hopping, thus forming a multi-hop network. As the head nodes needs to be turned on always, they are usually powered through a power socket. Let us now consider the detailed hardware setup of the system. Firstly, coming to the sensors part, there are four kinds of sensors that are possibly used in a parking system. They are magnetic sensors, ultrasound sensors, infrared, and video cameras. However, magnetic sensors are most sensitive and more immune to the environment factors such as rain. That's the reason why we chose magnetic sensors over the other three. Now let's see what type of mode can be used for our system. Ideally, a TI sensor tag is most suitable for our system as it has both magnetic and infrared sensors and is also compatible with Contiki. But Kuja doesn't provide simulation support to sensor tag as such. That's why we chose to simulate our system using T-Mode Sky. T-Mode Sky is an ultra low power wireless module which has a 10K SRAM and a 48K flash. The transceiver used in T-Mode Sky is 2.4 GHz chipcon. For easy installation, the sensor nodes are glued onto the floor and are battery powered. As for the head nodes, since they have to be always listening to the sensor nodes, they are designed in such a way that they can be plugged into a socket power supply.
Radio duty cycling is an important aspect of a wireless sensor network design, basically because it determines the sleep-wake cycle. So, by choosing the right duty cycling layer, it is possible to reduce energy consumption to a great extent. In our network, as said earlier, we have two types of nodes. One is a leaf node and the other is a cluster head. So let us consider the leaf nodes first. When should a leaf node transmit? The leaf node should transmit only when the magnetic sensor triggers an event that a car has come in or a car has gone out. When should the leaf node receive? Once the leaf node transmits to the cluster head, the cluster head sends an acknowledgement back to the leaf node, and the leaf node should receive this acknowledgement. So, based on these transmission and reception requirements, we came up with our own duty cycling layer for the leaf node. Our own RDC layer, instead of implementing periodic duty cycling, we turned the radio on only when the magnetic sensor events occurred. By doing this, we were able to achieve maximum energy efficiency for the leaf nodes. In case of the cluster head, there is no duty cycling, basically because it's socket powered and is always listening. The next part in the wireless sensor network design is the medium access layer. For medium access, we first need to figure out whether our network traffic is going to be low or moderate or high. If we consider the case of a parking system, all the nodes transmitting at the same time is a very rare case. So the network traffic is considered to be moderate here. Keeping this in mind, we chose carrier sense multiple access as our medium access mechanism. If we choose a contention-free protocol like TDMA or FDMA here, we might end up introducing unnecessary wait times. For example, if a node has a current event and it wants to transmit, then if there is no other node which has actually had an event, then this node has to unnecessarily wait for its turn to transmit that data. So we chose carrier sense multiple access, and in order to ensure that the data gets delivered, we introduced acknowledgements. So once a node sends a packet and the cluster head receives it, it sends an acknowledgement back. And if this acknowledgement is not received, the leaf node keeps on transmitting the data again. So in this way, we make sure that the data is not lost as well. Our network layer design is a hybrid model of both single hop communication and multi-hop communication. Single hop communication takes place between the leaf node and the cluster head, whereas multi-hop communication takes place between cluster heads and from the cluster head to the base station. So for this multi-hop communication, we decided to experiment with a lot of network layer mechanisms. So the first mechanism which we were interested in was flooding, basically because our network traffic is moderate. In case of flooding, what happens is, once the cluster head receives some data from the leaf node, the cluster head broadcasts that data to all its neighbors. And once those neighbors receive the data, they broadcast that data to all their neighbors. And those neighbors do the same thing. So this flooding goes on and on till the packets actually reach the destination node or the base station. So flooding works as long as the data traffic is moderate, but once the data traffic becomes high, flooding itself has a lot of data traffic because of broadcasting, and it might result in a lot of collisions and it might not work. And there's another problem which is inherent with flooding called implosion. By implosion, what we mean is, since a node broadcasts its data to all its neighbors and those neighbors also do the same, the node can receive the same data from multiple neighbors. So this is unnecessary. This introduces some unnecessary overhead, and that is what the implosion problem is. To overcome this implosion problem, a number of mechanisms were introduced. One of that is shared state. So that was the mechanism which we experimented with next. So in shared state, the implosion problem is flooding is overcome by using versions. So once the cluster head receives some data, it broadcasts to all its neighbors, similar to flooding. What these neighbors do is, once they receive the data, they check if the version of the data received is newer than the version that they have. If the version which is received is newer, they accept it and they broadcast it. If it is older or if it is the same, they do nothing. So by this, the implosion problem is alleviated to some extent. Next to shared state, there was one more mechanism which was introduced to alleviate the implosion problem in flooding. So that is called as gossiping. In gossiping, what happens is, once a cluster head receives some data from the leaf node, it chooses one random neighbor and transmits the data to it. And that neighbor in turn chooses one more random neighbor of itself and transmits. So eventually it reaches the destination. So we tried to implement all the three of them and compare how the packet density delivery ratio varies across the three mechanisms. In order to implement our parking system, we chose simulation over hardware for two reasons. The first reason is, in a parking system, we usually have a large number of parking lots and each slot is equipped with a sensor. This means we have a large number of sensor nodes, and to verify whether our network is working in such a behavior, we need to model our system using a large number of sensor nodes. This is difficult to implement in hardware because a maximum of 10 or 20 nodes can be verified in hardware implementation. Another reason is we wanted to implement 3 different network layer mechanisms and see which one is performing better in our scenario. So for this reason, simulation provides better options to compare and analyze like different networking mechanisms, and so we chose simulation. Now let's get into our implementation. So our code is basically organized into 3 different folders. So these are the folders into which our code is organized. So this flooding head, gossiping head, and chat state head. So our cluster nodes can use, cluster heads can use 3 different networking layer protocols. So these are the 3 protocols, and for each protocol we have a folder. And this leaf, it is the source code for the sensor node itself. So if you go into each folder, we can see that like there is a source code and we have a configuration file to say how our network parameters are configured, our MAC layer parameters like channel check rate are configured, and this is the make file. So now let's see the simulation. So in our simulation, before starting a simulation, I want to mention one major point. So in a real world, we usually have magnetic sensors to monitor the status of the parking lot. So if a car comes in or if a car goes out, the magnetic sensor sends a trigger to the controller, and based on that, it is sent to the base station. So to simulate this behavior, we used a button click in this simulator. So if a button is clicked once, it means a car entered, and if a button is clicked again, it means a car left. So coming to the network topology, so we have 6 nodes organized into a cluster with a cluster head. So if you see here, 1, 2, 3, 4, 5 and 6 belong to this cluster, for which 7 is a cluster head. And then if you see 8, 9, 10, 11, 12 and 13, those have the cluster head as 14. And these have the cluster head as 21. These 6 nodes have the cluster head as 28. These 6 nodes have the cluster node head as 35, and these have the cluster head as 42, and here 43 is our base station. The behavior we are expecting here is, if this sensor node detects an event, that is if a car comes in or a car goes out. In our case, if a button is clicked or if a button is clicked after it's clicked again, this needs to send the parking lot status to this head, and this head needs to forward it to the base station in a multi-hop mechanism. So first let us see how flooding behaves in such a scenario. Let's start the simulation. Now I'm going to click any one of these buttons to indicate that a car entered that parking lot. So let's consider that I click this button, that is a car entered here. So once a car entered here, let's see what are the series of actions that happen. So at 1, that is the sensor node, that node is sending the status to 7, that is it's sending a unicast message to 7, which means the state, and the message is that the status is 1, that is the parking lot is occupied. So if you see here, we also did an LED blink kind of thing to indicate that the parking lot is occupied or not. So here now the parking status is occupied, so the red LED is on. Now that from ID 1 we have sent a unicast message to 7. This needs to forward that message to the base station. Let's see how it did it. So at 7 it received the status from 1. So this 7 received the parking status from 1, and it broadcasted the message, that is, it simply flooded the message to all its neighbors, which is 21, 28, 35 and 42. So all of these have actually got the message and they have resent the message. So in flooding, basically once these nodes receive a message, they rebroadcast it. So they have broadcasted the message and eventually it has reached 43, that is the base station. Now let me show you what happens if a button is clicked again here, that is if a car leaves. So I am clicking the button again. You could see that the LED is turned off and that flooding mechanism happens again. So from ID 1, again we sent a unicast message is sent to 7 and again 7 has broadcasted it and those nodes have broadcasted it again. Now if you see, there's a difference in status. So first time it received the status as 1, the cluster had received the status as 1, and the second time it received the status as 0 and the message is delivered to the base station, which is 43. Now let me click the buttons in a few more places to show that if car enters in different parking lots, how that flooding behaves. So if you see, I click a button on 24, it's flooded and you can see that it's reaching this 43. Now I click a button here, it's flooded and it reaches 43. Again if I click here, flooding happens to all its neighbors and it reaches 43. If I click a button here, it's again flooded. So in all these cases we can trace how, suppose I clicked the button at 18, it sent a unicast message to cluster head, which is 21. So I click the button here, so it sent to 21 and 21 has broadcasted it to all its neighbors. All its neighbors received it and they broadcasted it, and if you see, eventually it reached the base station. The next network layer protocol we implemented is gossiping. In gossiping, if this cluster head receives the status from one of the sensor nodes, it forwards it to one random neighbor instead of flooding the entire network. So for this, if I click a button here, you can see that it's forwarded to only one random neighbor. So let's see the mode output. So unicast message is sent from 26 to 28, which is the head node, and after the cluster head received it, it forwards to a random neighbor. Since it forwarded to the random neighbor it forwarded was 43. So since it shows 43 as a random neighbor, it went directly to the base station. Now I'm clicking another button. So if it can be seen from this mode output that first, when the cluster head received the status, that is the ID 7 is a cluster head for this, it sent to a random neighbor. It did not flood it, it sent to a random neighbor 14, and from 14 it reached the base station. And let me show a few more cases. So here the packet is directly forwarded to 43, which is the base station. So sometimes if this random neighbor is chosen as the base station, the message is directly delivered to the base station. Otherwise it goes through multiple hops by using random neighbors. What we observe from gossiping is that the network traffic is reduced than flooding, but it takes a bit more time to reach the base station if some random neighbors are chosen, and it might take multiple hops than flooding to reach the base station. The third network layer protocol we implemented is shared state flooding. So shared state flooding is similar to flooding, except that the network traffic is a bit reduced by flooding to the next neighbor only if the version differs. For example, if this 14 receives a message from 7, then it will check if it already has that version. If it already has that version, it ignores that message. If it does not have that version, it will forward the message. So to do this, we implemented it by using versions for our data. So let's see how this works. Here I'm clicking a button. You can see that the same principle, like flooding is followed here. It's flooded to a neighbor, and this is flooded to a neighbor and reaches the base station. So if we can see that from the motor output. So ID7 sent. So ID5 is where the button click happened. There's a car entered or left, and it's sent to this cluster head, which is 7, and cluster head forwarded to all its neighbors by broadcast mechanism, and it reached the base station.
Let's now see the performance analysis. As we have three different network layer mechanisms, that is flooding, share state, gossiping, we have to compare the performance of these three and decide which is the best. In any normal scenario where there is moderate data traffic, the performance of all the three are quite close, and almost 99% of the data packets are delivered in all the three. So it's really difficult to quantitatively measure which mechanism is best in the normal cases where traffic is less. However, if we consider the worst case scenario wherein all the 33 parking spaces which we considered get empty or occupied at the same time, there's a remarkable difference in the performance of these three. This worst case scenario is possible whenever the parking spaces are extremely huge. For example, if we have some 1000 parking spaces, it is highly possible that 100 of these slots get occupied or vacant at the same time. We measure the performance in terms of end-to-end packet delivery ratio. The results were quite satisfying, and a clear difference between the three mechanisms could be observed. To mimic the worst case scenario, instead of using events which are triggered by a button, we used periodic data transfer for all the nodes to send the data at the same time.
Now in the simulation, you can see that all the nodes are transmitting at the same time, resulting in high network traffic. To measure PDR, we appended a packet ID information at the sending end, and at the receiving end, that is the node 43, we used a counter that counts the actual number of packets that are received. The window size which we considered is 10 packets. For example, in this case of gossiping, we can see that there is a sender packet count and there is a receiver packet count. Now, we can see that for the leaf node 13, the received packet ID is 6 and the total number of received counts for leaf 13 is 5. Using the above method, we calculated the PDR for the three different mechanisms for all the 36 nodes available. The results are as follows. If we compare the PDR of the above three, we can see that gossiping achieves higher average PDR, which is around 0.8, compared to that of share state, which is 0.7, compared to that of flooding, which is 0.6. So gossiping achieves the best PDR of all the three. This is for the worst case scenario. Now with respect to radio duty cycling, consider the following figure. In this, the nodes 7, 14 and 21 are the cluster heads which are always turned on. But if we consider the other nodes, they are turned on only when the event is triggered. Thereby, we optimize the duty cycling to the maximum extent that we can. To summarize this project, we designed a smart parking system using wireless sensor network. We designed a hybrid topology which has single hop and multi-hop network routing mechanisms. We achieved optimal radio duty cycling and reliable performance. From the leaf nodes to the head node, we used single hop, whereas from head nodes to the base station, we used multi-hop techniques. In multi-hop routing, we compared the performance of three flooding mechanisms. One is simple flooding, the other one is shared state, and the other one is gossiping. And we concluded that gossiping outperforms the other two when the network traffic is high.